Alright, so recall that we defined the sub-Gaussian random variable using a set of equivalent conditions. The most important being that the expectation of x square by some constant square should be less than or equal to 2, and this should happen for some finite constant k. Alright, and we extended the same ideas. We saw that something similar holds for sub-exponential distributions, that is those distributions for which the tail does not decay as fast as a sub-Gaussian, but it decays at least exponential in delta. Alright, so for any t greater than 0, the probability that mod x is greater than or equal to t is upper bounded by e to the minus t times some constant. Unlike the sub-Gaussian case, where it decayed as e to the minus t square times some constant. So, just as we define the sub-Gaussian norm, we can also define the sub-exponential norm as the smallest k positive for which the expectation of mod x by k is less than or equal to 2. That is, we had this property 4, the smallest constant for which this property 4 holds is what we call the sub-exponential norm. And just as we did for the sub-Gaussian case, we can prove that this satisfies all the three properties of the norm. So, the norm of alpha times x is mod alpha times the norm of x, and it also satisfies a triangle inequality, and the sub-exponential norm is strictly positive for any non-zero random variable. Right? And we saw towards the end, we saw an interesting property that if x is sub-Gaussian, then x square is sub-exponential. And the sub-exponential norm of x square is just equal to the sub-Gaussian norm of x the whole square. Right. So in today's class, we'll make use of these properties. We'll see a concentration inequality for sub-exponential random variables, similar to the Herfding's inequality that we saw for sub-Gaussian random variables. And we'll use that to analyze what is called dimensionality reduction, which is a very powerful tool used in data science and machine learning. Okay. So, the property that we saw is that if x is sub-Gaussian, then x square is sub-exponential, right? And the another property that, so we'll see some more interesting properties. I leave this as an exercise, which is that if x and y are sub-Gaussian, x and y need not be independent of each other. Then their product xy is sub-exponential. And you can show that the sub-exponential norm of xy sub-exponential norm of xy is at most the sub-Gaussian norm of x times the sub-Gaussian norm of y. And notice that so we anyway have just by the fact that the sub-exponential norm is a norm, we have that if x and y are sub-exponential, again these need not be independent of each other, then the sub-exponential norm of, let's say, alpha x plus beta y is upper bounded by mod alpha times the sub-exponential norm of x plus mod beta times the sub-exponential norm of y.
So it's y psi 1, psi 2,
Which one?
x, y are subgaussian and then x, y is subexponential.
Yes. I didn't get the question.
I didn't understand that statement, mod of x, y.
So if x and y are arbitrary subgaussian random variables, then the product of these two random variables, x times y, is a sub-exponential random variable. And the sub-exponential norm of x times y is equal to the subgaussian norm of x times the subgaussian norm of y. For example, you could just take x equal to y, right? So in that case, the sub-exponential norm of x square is upper bounded by the subgaussian norm of x times the subgaussian norm of x, which is just the subgaussian norm of x the whole square, which is what we saw earlier. Right? But this is sort of a generalization of the previous statement that previously we showed that if x is subgaussian, then x square is sub-exponential. Now what we're saying is that if x and y are subgaussian, then xy is sub-exponential.
So if you can speaking, just x is on subgaussian, which is again with subgaussian
Correct.
rate.
Yes.
Y is also subgaussian decay.
Correct.
So their product is sub-exponential decay, but
Correct.
it is less than product of two subgaussian decays.
So basically it decays exponentially, but then at what rate is the exponential decay, or what is the exponent corresponding to the exponential decay, right? So over here, if you look at the random variable xy, then this decays as e to the minus t times k, but what is this k equal to? Is something that is smaller than the product of the subgaussian norms. That's all that this is saying.
Sir, if norm is less, that means the decay is faster?
The norm is less means that the decay is faster, right? Because if the norm is less, then it means that this quantity is small, which means that 1 by that quantity is large. So e to the minus something is small. Right? So it decays much more faster. But how it decays as a function of t? So remember that k1 is purely dependent on the distribution. Alright? So it depends on the distribution of x. If you're looking at the tail decay of x times y, then this k depends purely on the distribution. Right? But as a function of t, it still decays as e to the minus some constant times t.
So, sir, product of two subgaussians decays faster?
So it decays slower than a subgaussian for large enough t. Right. Any other questions? Okay, so here's another exercise, which is that you know that if x is, let's say, subgaussian, right, and let's say that expectation of x, which is potentially non-zero, right, what can you say about expectation of x if you treat this as a random variable? It's a constant random variable. what is expectation of x? Is that also subgaussian? Yeah? Yes? No?
Then how can expectation of x be a random variable?
It's a constant, right? It's a constant random variable. It's a trivial random variable in that sense. Right? What can you say about a constant valued random variable?
It doesn't even decay.
Correct. So is it subgaussian?
If it's 0, it's 0, yes.
What if it, let's say x equal to 1 with probability 1? Is this a subgaussian random variable? Yes, right? In fact, we showed something even more powerful. Any bounded random variable is subgaussian. Right? A constant random variable in particular is a trivial example of a bounded random variable. Right? So, and in fact, you can see that if it's a constant, then the tail decay is the fastest possible in a constant random variable. Right? As soon as you move away from the expectation, it's equal to 0. Right? That's the fastest rate of decay you can ever have. Right? So expectation of x is, if you treat that as a random variable, and that is also subgaussian. But what we are more interested in is, what about x minus expectation of x? So x is subgaussian, expectation of x is a constant, right? Expectation of x may or may not be equal to 0. But in many cases, we are interested in the centered random variable, x minus expectation of x. So what can you say about this? Is this a subgaussian random variable? It is, right? It is also a subgaussian random variable. But what you can show is that the subgaussian norm of x minus expectation of x can be upper bounded by some universal constant times the subgaussian norm of x. Okay, so I leave this as an exercise. This is particularly useful. You can also show that if x is subexponential, then of course expectation of x is subgaussian and therefore also subexponential. X minus expectation of x is also subexponential, and the subexponential norm is again less than or equal to some universal constant times the subexponential norm of x. So throughout, whenever I use, let's say, c, it's going to be some universal constant, and I'll not be careful about saying that, for example, in this case, this universal constant is different from this universal constant, but hopefully that's understood from context. All right. Here is another important fact that we'll make use of in just a little bit, and that is if x is subgaussian and expectation of x equal to 0, then the subgaussian norm of x squared is lower bounded by some universal constant times the variance of x. All right. And this is something, again, it follows. It's a straightforward application of property 2 that we had for subgaussian random variables. Right, if you look at this, let's take property 2 and take p equal to 2, right? If I take p equal to 2, the left hand side is just square root the standard deviation, right? The standard deviation is lower bounded by some universal constant times the subgaussian norm times square root of p, which is root 2, right? So the standard deviation is a lower bound for some universal constant times the subgaussian norm. Right, that's all that we are saying here. So, which means that if the variance is large, then the subgaussian norm is also large. Right? The same holds true for the subexponential norm as well.
So won't this hold even if expectation of x is not equal to 0?
Then it's not so straightforward, because remember that property 2 only tells you something about the second moment, right? And the second moment is what in terms of the variance? Correct. So the variance is equal to expectation of x square minus expectation of x the whole square. So now the lower bound is no longer a universal constant. So this quantity is anyway lower bounded by some universal constant times the second moment, but then it won't be lower bounded by some constant times the variance, because then you also have a plus expectation of x the whole square, which depends on the distribution. Correct, but remember that it no longer depends, it's a constant but depends on the, for example, you can have a small variance and a very large expectation. Right? You just resend, instead of taking the mean to be something small, you could just shift it arbitrarily far away from 0. So then this lower bound no longer holds. Right? So you need to be careful. All right. So the main advantage of of these observations over here is that if x is a, let's say, we're obviously interested in not just random variables but random vectors, right? Typically high dimensional random vectors. And the observation that x square is subexponential or xy is subexponential means that the L2 norm square of a random vector turns out to be subexponential, and similarly the inner product of two independent subgaussian random vectors is subexponential. So now we can derive concentration inequalities not just for sums and averages, but also for norms as well as inner products. So first I'll state a very general concentration inequality. I won't prove this, but rather we'll use this inequality for a couple of applications. So this is the equivalent of the Hoeffding's inequality, but for sub-exponential random variables. So if we have independent random variables x1 through xn are independent sub-exponential, and we'll assume that these are centered random variables, so the expectation of xi is equal to 0 for all I, and let's assume that A is an arbitrary real vector. So it's a constant real vector. It's not a random vector, it's a constant vector. Then for all delta greater than 0, we can derive a tail bound on summation I equal to 1 to n ai xi greater than or equal to delta. Now this exhibits the kind of tail behavior that we saw for the Poisson distribution. For small delta, this probability decays as delta square. For large delta, it decays as e to the minus delta. So this is 2 times e to the power of minus some universal constant times the minimum of delta square by summation I equal to 1 to n ai square times the subexponential norm of xi square and delta by the max over I of the subexponential norm of xi. Right, so basically for very small delta, this term will dominate. For large delta, this term dominates. That's right. There should be an A. It's supposed to be AI times the subgaussian, the subexponential norm of xi. Okay. So this immediately gives us a concentration bound for the norm square of a Gaussian random variable or any sub-Gaussian random variable. So if, let's say, x1 through xn, let me call this the vector, the random vector x, is let's see, has independent subgaussian components, then the L2 norm square of x is subexponential. And again, just using Bernstein's inequality, so okay, let's maybe do this step by step. So the L2 norm square of x is subexponential, but really what we are interested in is the center. If I want to apply Bernstein's inequality, I have to first make sure that the random variables are centered, that is, the expectation is equal to 0, right? So then, since the L2 norm square is subexponential, this implies that the L2 norm square minus expectation of the L2 norm square, this is also subexponential. And in any case, the subexponential norm of this is different from the subexponential norm of this by some universal constant, some multiplicative universal constant. Right? So as long as we're not terribly worried about this constant sitting over there, it's some universal constant, but as long as we're not worried about this still continues to hold. I can still apply the same inequality. Inequality would hold with a slightly different universal constant. Right? So the probability that the L2 norm square of x minus expectation of the L2 norm square of x, probability that this is greater than or equal to delta, decays exponentially in as minus some constant times the min of delta square by the subgaussian norm square times delta by the maximum. Sorry, this should be to the power 4. The subgaussian norm square. Right? Because remember that the subexponential norm of a random variable, of the subexponential norm of x square is the subgaussian norm the whole square. Right? So if I use this particular inequality over here, this is the subexponential norm of the random variable whole square, which is, remember that in this case I'm replacing xi with xi square. So therefore this would be the subgaussian norm of xi whole to the power 4. Right? So this automatically gives me a tail bound on the L2 norm square of a random variable, of a random vector, sorry.
Why does constant change?
Because I'm using the bound for x minus expectation of x, or x square minus expectation x whole square.
You're still using the previous
Which one?
constant.
Correct, because this is also sub-exponential, but the sub-exponential norm of this is at most some constant times the sub-exponential norm of this. So essentially it would be this right hand side, but there would be some another universal constant in the denominator which I'm absorbing over here. So that is why the universal constant here would be different than this over here.
Sir, why would we need tail probability of
Why would we need tail probability of?
norm, L2 norm?
We'll see that in just give me a few minutes. All right,
Should there be a 2 in front?
correct. There should be a 2. All right. But even before we sort of proceed, let's sort of stare at this inequality and try to interpret it to see what happens. Right. So this is basically saying that if the L2, so let me rewrite this in the following manner. Let me take delta equal to the expected, or let's take the example of a Gaussian, just to be a little more concrete. So assume that x is an IID Gaussian. So it's a Gaussian vector with IID 0 mean sigma square variance components. All right. In this case, what is expected value of the L2 norm square? Yeah.
It varies.
Think you're close, but something missing. It's n times the variance, right? So this is expectation of sum of I xi square, which is n times the variance. Alright. And we also saw what the subgaussian norm square is. The subgaussian norm square is whatever. Maybe I think it was 8 by 3 sigma square, but it's some universal constant times sigma square. Right? So the probability that the L2 norm square minus n times sigma square is greater than or equal to, let me say, n times delta. Right? This is less than or equal to, let me call this epsilon. So I'm taking delta to be n times epsilon. Just to understand what this means. So here's a geometric picture, but of course in 2 dimensions. Right, so this is, you can consider the ball of radius or a sphere of radius root n sigma square, and I can construct a thin shell of width square root n times epsilon around this sphere. increasing y. This doesn't know, but yeah. Right, so basically this is a sphere of radius square root n times sigma square. I'll look at a thin shell around this of width the thickness of this shell is 2 times root n epsilon. Right? Epsilon is something very, very small. Okay. So the left hand side asks, what is the probability that if I take an IID Gaussian random vector, then most of the probability, or what is the probability that it lies in this very thin shell? Okay. I can make epsilon arbitrarily small, arbitrarily close to 0. Alright. If you were looking at just 2 dimensions, if I took a thin shell of radius, around radius, let's say 2 sigma square, or root 2 times sigma, what would be the probability that the random vector would lie in this shell as I made epsilon really, really small? What does the 2-dimensional Gaussian PDF look like? Yeah, it's a bell-shaped curve, right? Where is most of the probability lying? Close to the center, right? So much of the probability is close to 0. As you go away from 0, the probability is becoming smaller and smaller, right? But here I'm asking for something else, right? I'm asking what is the probability that the random vector, I draw a random vector and it lies in some very thin shell of radius square root n times sigma square. So this is like really far away from the center. Right? Square root, as n becomes large, root n sigma square is getting farther and farther away from the center. Right? And I can choose this epsilon to be arbitrarily small, so it's still a constant. The order of thickness of this shell is still of the order square root of n, but I can control the thickness using epsilon. I can make it arbitrarily small. Right? Even then, if I apply Bernstein's inequality, I get that this is upper bounded by 2 times e raised to minus some constant times min of, remember delta is n times epsilon, so it's n square times epsilon square divided by the denominator is sum over I xi, the summation over I xi to the power 4, right? The subgaussian norm of xi whole to the power 4. The subgaussian norm of xi square is equal to some constant times sigma square. So to the power 4 would be sigma to the power 4 times n. So the denominator is effectively some universal constant times n sigma square, comma n epsilon divided by max over I of the subgaussian norm square of xi. This would just be sigma I square, or sigma square. Right? So effectively I can make this epsilon to be arbitrarily small, but even then the right hand side tends to 0 exponentially fast. right? Even if I take, let's say, epsilon to be dependent on n, let's say I choose epsilon to be n divided by log n, which means what is the probability that x does not lie in a thin shell of thickness log n, right? That probability also decays with n. As n tends to infinity, this decays polynomially in n. Right? So unlike our conventional intuition, what is happening in 2 dimensions, where much of the Gaussian probability is centered around 0, in high dimensions something totally different happens. Much of the probability is not concentrated around 0, but rather much of the probability is concentrated in a thin shell far away from the origin, and with a thickness in a strip of very small radius. Right?
So, you're modeling the probability as like distance from the center instead of except by coordinate.
I'm sorry?
We are modeling the probability as distance from the mean.
So basically it's just an IID random vector, right? Gaussian random vector. And I want to know where most of the probability of this distribution lies. Right? In 2 dimensions, most of the probability of a 2-dimensional Gaussian random vector lies close to the origin. If you take 1 dimension, again, most of the probability lies close to the origin. Right? The probability goes to 0 as you go farther and farther away from the origin. Whereas something counterintuitive is happening as the number of dimensions becomes very, very large. It is that most of the probability is lying in a thin shell.
Isn't this norm?
Which?
This equation that you're using. Is
Correct.
this a norm, right?
Correct, yes.
Probability of.
But what does it mean for the norm to be very close to something? It means that x, the length of the random vector, is very close to this. Right? You can we're basically going from Cartesian coordinates to polar coordinates in some sense. Right? And there's a reason why this is happening. I mean, even if you think about what the density is, if you think about the d-dimensional Gaussian density or the n-dimensional Gaussian density, again the density is the maximum when x is equal to 0. Right? So you would expect the probability to concentrate close to 0, but that's not happening over here.
But then we are not finding probability of x, right? We are doing probability of norm or.
Correct. But then my claim, just stare at this quantity. This is equal to the probability that the random vector x lies within a thin shell of thickness 2 root n epsilon, and the radius of this shell is root n sigma square. Right? Is this equivalence clear? Right? The probability that x lies in this thin shell is the same as the probability that x has norm close to n times sigma square, or norm square close to n times sigma square. Right? So this seems very, very counterintuitive, despite the fact that if you look at the density of the Gaussian, of the n-dimensional Gaussian, it is radially decreasing, right? Because the density of the Gaussian is some constant times e to the minus norm x square divided by sigma square. All right? So what is happening over here? What is happening over here is that our geometric intuition for high dimensions is completely out of sync with what happens in 2 dimensions or 3 dimensions or 1 dimension. What is happening? Yeah.
So that is the probability that that vector is outside that shell, right? It's greater than or equal to dimension.
Correct. Yeah. So this is equal to the probability that x is not in this shell. Right. That's right. So the probability, so with high probability, so with very high probability, x is going to lie within this thin shell. Right? I just, sorry if I sort of confused you. So basically most of the probability is in this thin shell and very little probability is outside this thin shell. Now it's natural to expect that the probability as you go away is very small, right? That's believable. But what is perhaps less intuitive is why the probability of lying within this ball of radius square root n sigma square minus n epsilon is small, right? Because effectively a corollary is that the probability that the L2 norm square is less than n sigma square or n sigma square times 1 minus say epsilon. This tends to 0 as n tends to infinity. Right? So the probability that you lie somewhere in here, the probability that you lie somewhere in here is also vanishing in n. Right? Is this statement clear? It seems counterintuitive, but hopefully the statement is clear. And the reason why this is happening is because the volume of this particular region is in fact negligible compared to the volume of this shell. If you recall from your first homework assignment, there's a problem where you calculated volumes of balls. Alright? So if you look at the volume of, you can exactly try to compute or at least try to upper bound the volume of this thin shell and compare that with the volume of this ball of this particular squared radius. And you'll see that the volume of that shell is much larger compared to the volume of a ball of this squared radius. Right? Which is not intuitive because that does not happen in 2 dimensions. In 2 dimensions, the thickness of, if you take a ball, much of the volume is at the center, right? It's not close to the surface. But as you go towards higher dimensions, most of the volume is close to the surface of the ball, and there's very volume in the interior of the ball. All right, so that's something that keeps coming up as you go to higher dimensions, particularly when you analyze problems in very high dimensional spaces, but which does not conform with our basic intuition of 2 and 3 dimensional spaces. All right? And that is in fact what makes problems in high dimensions hard. This is sometimes referred to as the curse of dimensionality. If you're dealing with very high dimensional objects, then a lot of counterintuitive things can happen. All right? So as you go towards higher dimensions, you get both benefits as well as disadvantages. The benefits are that you have these phenomena of concentration happening. But the disadvantages are that all of this can be completely out of sync with what we expect to happen in low dimensional spaces. All right. Any questions? Okay. So now what we saw is that if x is, if the vector x has subgaussian components, then the norm square is subexponential, right? But what about the norm itself? Can we say something about the norm? Has IID subgaussian components. Let's make some more assumptions for convenience. Let's assume that expectation of xi equal to 0. We'll also assume that each component has unit variance, but they need not be IID. They have to be independent. So let's say that Ki is the subgaussian norm of xi. Alright. What can we say about the centered variable, the L2 norm of x minus square root of n? Let me call this y. Yeah? It's a random variable, right? So you would expect that the L2 norm of x should be very close to square root of n. Right? But can we say something more about this random variable? Is this subgaussian? Is it subexponential or something else? What would you expect?
If its square is subexponential, then we could expect the norm itself to be subgaussian.
Correct. So this in fact is subgaussian. And the subgaussian norm of y happens to be at most some universal constant times the largest ki. I'm sorry, ki square. Okay, remember that on the left hand side I have the subgaussian norm. This is upper bounded by some constant times the max over I subgaussian norm squared of xi. It's an upper bound. So let's see why this is the case. So firstly, we know that xi square minus 1 is subexponential. Right?
Does it not depend on the number of dimensions?
Which one?
Subgaussian norm of y.
The subgaussian norm of y, in fact, does not depend on the number of dimensions. So, um, so xi square minus 1 is sub-exponential, right? So this is, and that's because xi is subgaussian, xi square is sub-exponential. Therefore, xi square minus 1 is sub-exponential. What can I say about the sub-exponential norm of xi square minus 1 in terms of the sub-Gaussian norm square of xi? Some universal constant times the sub-Gaussian norm of xi, the whole square. Right? Okay. So now, since this holds, I can therefore use Bernstein's inequality for this particular random variable. Right, so the probability that the L2 norm squared of x minus n is greater than or equal to some n times, let me call it delta, is less than or equal to 2 times e to the power of minus some constant times n square delta square by sum over I ki square, sorry, ki power 4 and n delta by ki square. Okay, and this is less than or equal to 2 times e to the power of minus some constant times n square delta square by n times the largest ki, let me call that ki max, k max to the power 4. There should be a max. N delta by k max square. Right? Now, here is what we know. I claim that k max is greater than or equal to some universal constant c prime. why is that? This is because ki is lower bounded by some universal constant times the variance, right? We showed that previously. I'm using this property over here, and I took the variance to all be equal to 1. Alright, so the subgaussian norm square is lower bounded by some universal constant. So basically, why I want this is because k max to the power 4 is greater than or equal to some universal constant times k max square. Basically, I have two terms over here. One that involves delta square by k max to the power 4, the other involves delta by k max square, and I want to remove I want to take the denominator outside this min. Okay, that's the only reason. So this is upper bounded by 2 times e to the power minus some universal constant times, I can take n by k max to the power 4 outside, times the min of delta square and delta. Right? Is this okay? Fine. So I have this, let's keep it aside. The next is this observation. For any number z, mod z minus 1 is greater than or equal to delta, implies that mod z square minus 1 is lower bounded by max of between delta and delta square. Okay. I'll leave this as an exercise. So if I use this, right? So this is some event. Let's call this event A. And this is some other event. Let's call this event B. So if event A happens, then you're sure that event B happens. So then what can you say about the probability of event A versus the probability of event B? So probability of event A should be less than or equal to the probability of event B. Right? So if I just use this then the probability that the L2 norm of x minus root n greater than or equal to root n times epsilon for some epsilon positive this is less than or equal to the probability that the L2 norm squared of x minus n deviates from n times epsilon square, deviates from n by an amount n times epsilon square. Right? I'm sorry, so I have to be a little careful over here. Since I'm using this, it deviates by an amount n times max of epsilon and epsilon square. Right? So basically here I've used this particular fact. So this is event B and this is event A. So just using the Bernstein's inequality, what I had here, if I apply using 1, this is less than or equal to 2 times e to the power minus some constant times n divided by k max to the power 4 of min of delta square, where delta is equal to max of epsilon square. Okay. So basically what I have is min of max epsilon square and max epsilon square epsilon power 4. And I claim that this is equal to, always equal to epsilon square. Right? Because if epsilon is less than 1, then epsilon is greater than epsilon square is greater than epsilon power 4. So if epsilon is less than 1, then this is epsilon and this is epsilon square, and the smaller one is epsilon square, so it will be equal to epsilon square. If epsilon is greater than 1, then epsilon is less than epsilon square is less than epsilon power 4. So this is going to be epsilon square, this is going to be epsilon power 4, and the smaller one of those two is again epsilon square. Alright? Just substituting this, I get probability that L2 norm of x minus square root of n greater than or equal to square root n times epsilon is less than or equal to 2 times e to the power minus constant times n epsilon square divided by k max to the power 4. Right? And this holds true for every epsilon greater than 0. So basically for every, just by changing the variables, norm x minus square root of n greater than or equal to some delta prime is less than or equal to 2 times e to the power minus some universal constant times delta prime square divided by k max to the power 4. Right? So just using property 1 of the subgaussian random variables, you see that the right hand side is a tail bound that decays as delta prime square, and therefore it's subgaussian, and the subgaussian norm is some universal constant times k max square. Okay, is this okay? Any questions? So now let's see an application of this to dimensionality reduction. All right. So what is the problem of dimensionality reduction? We are given a collection of points in very high dimensional space. Let me call them x1, x2 up to xn. So each xi is an arbitrary vector in capital D dimensional space where D can be arbitrarily large. Okay. And the goal is, maybe I want to do, say, k-means clustering or some form of clustering, distance-based clustering for these set of points. Okay. So if I want to do, let's say, k-means clustering, then at the very minimum, I should first compute pairwise distances between these points. Correct? What would be the complexity, rough order of complexity for computing pairwise distances between these pair of points? N square times d. Alright? So what I'm more interested in is, of course, it's order n square in terms of number of points. But again, as I said, the dimension is very large. In particular, d could be much, much larger than n square, in which case d now starts to dominate. Alright? So the complexity of computing pairwise distances is order n square times d, which could be very, very large. Alright? My goal is to somehow reduce this complexity. Okay, and how I'll try to do that is by first bringing these xi's down to a lower dimensional space, and then trying to do, let's say, k-means clustering, whatever, on this lower dimensional space. Okay, so I'll do this in two steps. First, I look for some function g from Rd to are little d, where d is hopefully much smaller than capital D. Okay. Remember, I'm operating in the regime where capital D is much larger than n. Okay, that's the assumption. Very high dimensional space and large number of points. And the second step, I'll do whatever I want to find pairwise. I can run any algorithm. K-means clustering is one such example, but maybe I'm interested in doing a very large number of computations based purely on pairwise distances between in this lower dimensional space. Compute distances in RD. And when I say distances, it's distance between pairs of points. So basically between g of xi and g of xj. Okay. So hopefully now the complexity in this lower dimensional space, computing a pairwise distance takes only complexity little d instead of capital D. That's one advantage. I can compute pairwise distances much more easily. But also, let's suppose I want to store this data set in some way, right? Because I may want to do something more later on. Then it's pretty easy because now the storage complexity is also little d instead of capital D. So I've reduced space. I've also reduced computational complexity. But all of that holds true only if pairwise distances in the lower dimensional space is still roughly the same as the pairwise distances in the higher dimensional space. Otherwise, all of this reduction is completely pointless. Right? So we want a G such that the distance between any pair of points is at least close to the distance in the higher dimensional space. Plus epsilon Alright, so such a map is called an epsilon isometry. An isometry is basically a map that preserves pairwise distances. Here we are asking something, we're relaxing this constraint. We only want to approximately make sure that the pairwise distances are preserved. Alright? So a relatively easy consequence of all that we've seen previously is the following. So it's a lemma due to Johnson and Lindenstrass, and it says that if I take g of x to be a times x, basically I'm using a linear map, a linear projection, where A is a random matrix with IID Gaussian entries 0, 1 by n, or 1 by d, then 1 by square root of d, then, and I take d to be some constant times k to the power 4 divided by epsilon square. So in fact, I can take, this doesn't have to be Gaussian, it can be any subgaussian matrix, a matrix with IID subgaussian entries. K to the 4 times log n by root delta. So basically I choose a D that is completely independent of capital D. Right? The capital D could be really large, but this little d, the dimension of the lower, where I'm projecting it down to, is much smaller, and it's independent of capital D. It depends on n, but independent of capital D. The probability that A is not, and let's put the positive way, is an epsilon isometry is at least 1 minus delta. So with very high probability, a random Gaussian matrix or a random sub-Gaussian matrix is an epsilon isometry. Right? So very powerful tool, because irrespective of the dimension of the original space, I can bring it down to a much lower dimensional space, completely independent of capital D. But of course, it now depends on n. Alright. So again, we have essentially have all of the tools that are required to prove this, but maybe we'll do this in the next class. It's a relatively easy consequence of this property that we've seen over here and a union bound. So basically this, along with the union bound between pairs of points, will give us the Johnson-Dunning-Strauss lemma. But maybe we'll complete that in the next class. Alright, so let's stop here.